Okay, let's return to our test example. Remember, we had given the probability distribution for answering the questions as getting 0 correct, probability 27 out of 64, 1 correct 27 out of 64, 2 correct 9 out of 64, and 3 correct 1 out of 64. Now, if we multiply 0 times its probability 27 out of 64, 1 times its probability 27 out of 64, and then 2 times its probability 9 out of 64, then 3 times its probability 1 out of 64, then I'll actually get 48 out of 64, or 3/4, which reduces to 0.75. So we would expect to average getting less than 1 question correct per trial. So in other words, we would average getting 3/4 of a correction correct. And so remember, a trial would be to answer all 3 questions. Okay, so we would expect, if we did this, if we tried this experiment, guessing on 3 questions 100 times, we would expect to get a total of 75 of those questions correct, because 100 times 0.75 is 75 correct questions. Now, note that these expected values are not probabilities. They actually can be greater than 1 or less than zeros, and you can write them as decimals or fractions. Okay, so let's look at another one. Suppose 2 coins are tossed and we wish to observe the number of heads that occur. Since that's what we want to observe, we're going to let x represent the number of heads that can occur on a given trial. Well, remember, the possible values, if you toss 2 coins, you could get no heads, 1 head, or 2 heads. So now let's figure out the probabilities of getting no head, 1 head, or 2 heads. Well, if you look at the sample space, there's only 4 possibilities. And the only way to get no heads would be to get both tails. So that's got a 1 out of 4 probability. And then the only way to get 1 head would be to either get head tails or tail heads. So that has a 2 out of 4 probability, or 1/2. And the probability of getting 2 heads would be, there's only 1 out of 4 ways that could happen. So that probability would be 1/4. Now, if we want to find the expected number of heads, we just take 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4, and then we add those together, and when we add them together we get 1/2 plus 1/2, which is 1. Well, that kind of makes sense in that example. You can't always make sense out of these expected values, but this one makes sense because if you toss 2 coins, on average what you would expect would be to average 1 head per trial and 1 head per trial. So that one kind of makes sense. Now, let's look at the next example. So this example, suppose we select 3 cards from a deck and we want to observe the number of face cards. Well, since I'm observing the number of face cards, I'm going to let the random variable represent the number of face cards. Well, if you draw 3 cards from a deck, you can get no face card, 1 face card, 2 face card, or 3 face cards. Well, remember, the probability of getting these results has to be out of the total number of 3-card hands, which is 22,100. So now let's talk about the probability of getting no face cards. Well, the probability of getting no face cards would mean that I choose all 3 cards from the 40 non-face cards. So the probability of that happening would be 40 choose 3 over 52 choose 3, which is 0.4471. Now the probability of getting 1 face card would mean that from the 12 face cards I choose 1, and from the 40 non-face cards I choose 2. And if you multiply that together and then divide by 52 choose 3, you get 0.4235. And then the probability of getting 2 face cards would be, out of the 12 face cards choose 2, and out of the 40 non-face cards choose 1, and then divide that by the same denominator and you get 0.1195. Now I had a typo on this one, so I've corrected it. The probability of getting 3 face cards would be, out of the 12 face cards you got to choose all 3, and again, you don't have to put the 40 choose 0, but I'm just showing you you're going to choose none of the non-face cards. All the cards you choose here are going to be face cards. So you can take 12 choose 3 divided by 52 choose 3 and get 0.01. Now, if I put these probabilities in the probability distribution table with their corresponding x values, then I get 0 with 0.4471 probability, 1 with 0.4235 probability, 2 with 0.1195 probability, and 3 with a 0.01 probability. And of course, if you add these four up, they should add up approximately to 1. If they don't add up exactly to 1, it's just because of the rounding. Okay, so now to find the expected number of face cards, just multiply 0 times 0.4471, 1 times 0.4235, 2 times 0.1195, 3 times 0.01, and then add them all up, and you'll get 0.6925, or if you want to round it to 2 decimals, about 0.69. Now what that means is that if you do this trial 100 times, you would expect, just multiply 100 times the expected value per trial, and you would expect to get a total of 69 face cards in this experiment. Okay, in the next experiment, suppose that 2 four-sided dice are rolled and you wish to observe their sum. Well, for four-sided die, the lowest roll you could get is 1, 1. The highest roll would be 4, 4. So you could only get sums 2 through 8. And remember, there's 16 ways to roll 2 four-sided die, because there's 4 ways to roll the first die, 4 ways to roll the second die, so that gives you 16. Now you could write out all the possibilities. 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, and so on. But the probabilities of rolling a sum of 2, there's only one way that would happen, and that would be if you roll a 1, 1. The probability of rolling a 3, there's 2 ways that would happen, so the probability would be 2 out of 16, which is 1/8. The probability of rolling a sum of 4 would be, there would be 3 out of 16 ways that could happen, and that would be if you rolled a 1, 3, a 3, 1, or a 2, 2. Probability of rolling a 5, there's 4 ways out of 16, so that would be 4, 1, 1, 4, 2, 3, or 3, 2, and so on. So you can do the other 3 and determine the probabilities are 3/16 for 6. The probability of getting a 7, sum of 7 is 1/8, and the probability of getting a sum of 8 would be 1 out of 16. So the probability distribution table for 2 through 8 has the following probabilities: 1/16, 2/16, 3/16, 4/16, and then it goes back down: 3/16, 2/16, 1/16. And then when you multiply each x by its corresponding probability, 2 times 1/16 plus 3 times 2/16 plus 4 times 3/16, and so on, and add them all up, you get 80 out of 16, which is 5. So that means you expect to average a sum of 5 if you roll these dice over and over and over. In other words, if you do the experiment a large number of times, you expect to average a sum of 5. Okay, let's do another example here. Example 4 says, suppose a random sample of 2 light bulbs is selected from a group of 8 bulbs that contain 3 defective. So basically, you've got to remember that you've got 3 bad bulbs in this sample, and bad, and you've got 5 good bulbs. So keep that in mind. 3 bad bulbs and 5 good bulbs. So we want to find the expected value of the number of defective bulbs. Basically, you can just say we want the expected number of defective bulbs here. So I'm going to let x be the random variable that's associated with the number of defective bulbs that will occur on a given trial. And now, since you're only going to take a sample size of 2 here, notice here you're only taking a sample size of 2, you can only get up to 2 bad bulbs. So the random variable x cannot go any higher than 2. So when you're setting up those values for the random variable there, that 0, 1, 2, make sure you consider 2 things. Number 1, your sample size. Obviously, the number cannot go higher than your sample size. And the other thing is what the random variable represents. Now in this case, the random variable represents the bad bulbs, which there are 3. So obviously the number couldn't go higher than 3, but since it can't go higher than 2 due to the sample size, then we don't have to worry about that. So what I need to do is I need to set up this distribution table for the probabilities. But in order to do that, obviously I know that x values can be 0, 1, or 2, but I need to get their probabilities. Well, the denominator is going to be the total number of samples possible. So that's going to be out of 8 bulbs, choose 2. So that's the total number of samples possible. And then the numerator, we have to figure out how many ways we can get a sample that has no bad bulbs in them for x equals 0. So out of the 3 bad bulbs, we got to choose none. And so that means out of the 5 good bulbs, both bulbs have to come from those. So we got to choose 2 out of those. And plug that into your calculator and get 0.3571. And then for 1 bad bulb, out of the 3 bad bulbs, we have to choose 1. And that means out of the 5 good bulbs, we have to have 1. So that we have a total of 2 bulbs. And then calculate this and divide it by 8, choose 2. And you'll get 0.5357. And then the probability of getting 2 bad bulbs, we have to say, well, how many ways can we get 2 bad bulbs out of 3? So we do 3, choose 2. And then out of 5 good bulbs, we're choosing none. And then again, we divide that by 8, choose 2 as well, and we get 0.1071. Now remember what I told you about these choose 0 factors. They equal 1, so you don't have to write them if you don't want to, but I just like writing them so you can see that we're going to have 2 bad bulbs and no good bulbs in this sample. And then over here we're going to have no bad bulbs and 2 good bulbs. So it's just something I like to do when I write these. Okay, then I put the 3 probabilities in my table, and then I calculate the expected value by just multiplying each pair. 0 times 0.3571, 1 times 0.5357, 2 times 0.1071, and I did those calculations down here, and then you add them together and you get 0.75. So basically, in a sample size that has 5 good bulbs and 3 bad bulbs, if you take a sample of 2, you're expected to average per trial less than 1 bad bulb per sample. You're supposed to average about 0.75 bad bulbs per sample. And now how this can come in handy is if you set up a certain tolerance level for these samples, and if you start averaging more than that particular tolerance level, then you might want to go back to your manufacturing process and make some changes or some improvements. Okay, I call this a challenge problem. In Texas Lotto, you actually select 6 numbers from the numbers 1 through 54, and obviously if you get all 6 you win the jackpot. And you can't choose repeated numbers, and the order doesn't matter, so the order they're drawn doesn't matter. So basically that just tells me that we can use combinations here. Now if I were to let x represent the number of possible matches I could get, well, obviously you could get anywhere from 0 of the numbers matching all the way to 6 numbers matching. So we can think of this as 6 good numbers and 48 bad numbers. We just don't know what the numbers are. So the probability of matching none would be 48 choose 6 out of 54 choose 6, which is 0.475. And the probability of matching 1 would be 6 choose 1, 48 choose 5. So that would be 1 good number and 5 bad numbers. So that's 0.398. Now you can read the rest of the calculations. Like here it's 6 choose 2 times 48 choose 4 for 2 good numbers. And so the rest of the calculations, you can freeze the video if you want to, and then you can read the rest of these calculations that I've got here. Now notice what I did. I put them in this table, and then I multiplied each x by its probability. And when I did that, and then added them all up to get the expected value, I got 0.667. Now what's interesting about that is the average person is going to match less than 1 number. So the average person is going to match about 0.7 of those numbers. But you don't make any money unless you match 3 or more. So you can see why this game is lucrative to the providers of the game. Okay, I'll do some more examples for this section on the next video.